topic is patrolling the border with striking conjecture.
Okay.
So first of all, I'll try to make it understandable to every layman, except especially to a layman like me. No groupoids, boxities, dimensional skeletons, etc. So in an expression n alpha plus beta, the symbol alpha is called the modulus and beta the shift. When a finite number of such sequences cover all positive integers exactly, it is an ECF, exactly covering family. Now, what does it mean to cover all positive integers exactly? It means that every positive integer appears, but only once in only one of these sequences. Now, there is a very interesting curiosity. When all the alpha are integers, then in every ECF, there must be two equal moduli. The simplest case is 2n plus 1. So the 2 appears twice, 2n, all even numbers, 2n plus 1, all odd numbers. Or for example, 2n, all the even numbers, 4n plus 1, all odd numbers congruent to 1 mod 4, and 4n plus 3. The late Ron Graham showed that this property also holds if all the moduli are irrational. That's very interesting. Let's go on. So the abstract is that the conjecture is about disjointness and coverings of integers. Now, we saw that in the integer case and in the irrational case, there are always two moduli that are the same. But here is the interesting point. There is a unique system of sequences involving consecutive powers of 2 with distinct moduli forming an ECF. One of our main results, when the powers of 2 are replaced by certain powers of any number bigger than t, then such sequences necessarily intersect. Another result, when 2 sequences intersect, there must be some missing numbers in the union of the sequences, since the reciprocals of all moduli sum to 1 by density considerations. I hope I'm still explaining things to the layman. Study the structure of this complementary sequence of missing numbers. Go on. More explicitly, conjecture A. There is a unique system, SI, integer part of Pn over alpha I over AI plus beta I, no, it's alpha I, distinct alpha I, where all the alpha I are consecutive powers of 2. That there exists such a system that has been shown by me some years ago, but the uniqueness is still missing. That's really the conjecture. that there's only one system in which the moduli are distinct, and it's unique, only that one. That's the conjecture. Now, usually in math, the rationals team up, if at all, with the integers. Yet here, the irrationals join in with the integers, because in both cases there are repeating moduli. Curiously, only the rationals stand out stubbornly according to conjecture A. Somewhere I saw the following sentence: number theory concerns the study of properties of the integers, rational numbers, and other structures that share similar features. In the present study, rational numbers do not share similar features as integers and irrationals.
Rational numbers are not as rational as usually believed, according to you.
Now, what does it say? I'm nearly deaf, Doron, and I can't, unfortunately, hear what you said.
Rational numbers are not as rational as they seem, according to you.
Rational numbers are not as rational as they seem to you.
Yes, you're right. Your remarks are always to the point. Thank you very much. So one of the main results is the following theorem. Sequences of the form, as you see here, Pn over alpha I plus beta I are disjoint in pairs if and only if alpha A equals to 2 with appropriate non-unique shifts. And P, the P that you see there in the integer part, is a common integer numerator for all the sequences and for all A. Why this choice of P? You see, we want to cut the cake into slices of size P over A to the M. Each slice occupied A to the M over P of the cake. So in order to cover the entire cake disjointly, we need that the sum of AI is equal to P, which holds precisely for the P we chose. So these are certainly necessary requirements to cut the cake into slices of these sizes P over A to the M. And so the cake is cut into disjoint pieces, and no crumbs of one piece enters into the other. Next slide, please. Are these necessary conditions also sufficient? It seems so. No crumbs of one piece, of one slice goes into the other, and every crumb is covered. That is to say, it appears in one of the slices. However, against all our guesses, these conditions are not sufficient. We need also that the cake is cut in distinct lines. Our feeling is that this is achieved when all the slices P over AI are in lowest terms. But this feeling needs to be proved. And this is a core of the proof of the theorem. For example, 1, 2, 3 satisfy 1/6 plus 2/6 plus 3/6 is 1, yet they are not moduli of an ECF. 2/6, 3/6 are not in lowest terms. In fact, a to the power m minus 1 over a minus 1, which we chose as the common numerator, is an integer not in lowest terms for a bigger than 2. I think that this explains the uniqueness of the power of 2 in the theorem, that only the power of 2 works and all the others do not work. The core is based on the powerful JRT, Japanese remainder theorem, due to Morikawa and Jamie Simpson. This JRT theorem cannot produce valid moduli, but it can verify their suitability. If you can guess some suitable moduli, then the theorem can validate them. But it's strong nevertheless. I would like to state it here, this nice, powerful theorem, but I promise to make my talk understandable to the layman. So I don't mention it, which I really would like to do. It's a beautiful theorem. Let's go on. Roughly, the striking conjecture states any decomposition of the positive integers into at least 3 sets of the form integer part n alpha I plus beta I with all moduli alpha I distinct satisfies this formula that alpha I is 2 to the m minus 1 over 2 to the I. And it is unique. No other moduli have this property of being distinct in an ECF. The cake can be cut into disjoint covering pieces, but the slices are also of different sizes, and there's only a single way to achieve this. If you think of an ordinary cake, there are certainly many, many ways to do it. But in our case, there's only a unique way to do that into disjoint covering slices, which are disjoint. So this is a conjecture, which is still unproven. It has been proven for up to 7 sequences that this must hold by several authors. And you can find the history of this and whoever did this in a paper by Robert Tiedemann from Holland. Let's go on. The new theorem says that above does not prove the conjecture. It only demonstrates that consecutive powers of 2 provide ECF, but there could be other systems, not necessarily involving powers of 2, also providing ECF. However, it provides surface support in proving the conjecture. And as I said, you can find the history and so on about the conjecture in a paper by Tiedemann, which is written down here in discrete mathematics. So I think I have tired you enough and not quite held the promise that I would make things completely understandable to the layman, but I hope that at least I myself now understand the theorem. So I will finish here. Thank you very much.
Any questions or comments?
So this conjecture has been proved for 6, but it's still open in general?
האם זה כבר הוכח על ידי מישהו, אבל אני לא יודעת מי.
The conjecture is still open, right? The general conjecture. ההשערה עדיין פתוחה.
I think they're frozen. There must be a problem with their connection.
You didn't hear me?
Can you hear us now?
Shaula, can you hear us?
I think there's some problem. On their side. Oh.
There is an answer from what to know.
Yeah, right now it says it's okay. I think they have left. What should we do? I should stop recording, right?